So we're going to look at a good example of net forces that has to deal with vector addition, so to speak, or the differences between the two vectors. So let's say that we have two forces. They're being applied to the center of mass of an object. We're specifying center of mass, meaning the object won't spin, so there's no force lost in rotation. The first applied force to the object is 6.71 newtons, and that's in the direction that is 63.4 degrees north of east. So the way I would read that direction base is I'm going north of the set direction. So if I look on the XY plane, east is pointing right on the positive X axis. And I then take my cursor and I move 63.5 degrees north of that. So this is the 63.4 degrees. Okay, so that's how I would read that direction. Then in the next case, the second force that is being applied to it is 2.11 newtons in the direction which is 18.43 degrees south of west. So that means I take the axis that is pointed west and I go down to the south direction 18.43 degrees. By taking these two vectors, I want to essentially get them and put them in from their polar coordinates, because that's what the form that they're given to me in. Polar coordinates meaning so for the first force, right? So let's call that force sub 1. That's equal to the radius component, which would be the 6.71 newtons in the direction of 63.43 degrees. That would be the consideration for my first polar coordinate. My second polar coordinate, if I put it in terms of polar coordinates. So this one is a little different. I have to specify. So the radius is still 2.11 newtons, but then I have to specify. So that angle, so I want us to think about, we always set this up as if it's on a unit circle. So my starting position, or 0 degrees, is on the positive X axis. So that would be in terms of northeast, west, south, that'd be east direction. So to read 18.43 degrees, that's south of west, I need to add 180 degrees to it if I'm reading it in terms of full polar coordinates, putting it on a unit circle. And when I add 183 degrees to it, I get that it is 198.43 degrees. So using those two things, I'm going to essentially also remember that in terms of components, my x component is equal to the radius times the cosine of theta. Or just look at how it's oriented on a unit circle. My y component is equal to the radius times the sine of theta. And then the radius, the magnitude of the radius. So you could say that the magnitude of r is equal to the square root of x squared plus y squared. And that's just Pythagorean's theorem for when we find the final vector. And then one more thing, we also know that theta, the angle, the final angle I'm going to end up with, is going to be the inverse tangent or arctangent of my opposite, which I'm saying is my y, over my adjacent, which is my x. So these equations are going to give me everything I need to know about this problem. So for the first case, for force 1, let's put it in its component form. So my x component, again, is going to be that radius, the 6.71 times the cosine of 63.4 degrees. And that's in the x hat or I hat, whatever notation you prefer to use, direction, plus my y component, which is going to be the same radius, 6.71 times the sine of 63.4 degrees. Then that's in the y hat direction. My second force, that's going to be 2.11. That's going to be the cosine now of 198.43 degrees in the x hat, plus 2.11 times the sine of 198.43 degrees in the y hat. And in terms of this, I would keep both signs positive. So you might be noting from the graph, my x direction and my y direction for that second force, they're both in the negative x and y for force 2. That's being taken into account by the fact that we did it in terms of 198 degrees instead of just 18 degrees. So you don't need to add another negative there. In fact, it would cancel itself out, wouldn't be correct. So when I have them in component form, at this point, I'm just adding like terms. So for my net force, I'm going to sum the x components and the y components. So it's going to be 6.71 cosine 63.4 x, sorry, not x hat yet, plus 2.11 cosine 198.43. That's all in my x hat direction. So plus my y hats, which are going to be the 6.71 sine 63.4, you get the idea, plus 2.11 sine 198.43, and that's my y hats. So I get my net force for the two components for the x's. It's going to be positive 3 minus, so it's plus a negative, or I could just say minus 2 roughly in the x hat. Plus, for my y components, I have 6 plus another negative, so just minus roughly about 2 over 3, or you could put 0.6667, however you want to do it. It's not required to do fractions. That's in the y hat component. So then F net is equal to 1 in the x hat, plus we could basically say that this is 5.33 in the y hat. And then for this point, I'm going to use these two equations to get my component form for the final vector into polar coordinates. So in terms of a magnitude and a direction. So the radius for my net force is going to equal the square root of this x squared and y squared. So it's going to be 1 squared plus 5.33 squared. I get that it is roughly 5.43. And what is the unit for this? This is newtons, right? So it's a net force. This is the magnitude of newtons. It should never be a negative number, the radius. It's an absolute value of magnitude. So because we take into account, what does that negative mean? It's direction based. We take into account the direction when we take into account the angle for polar coordinates. So for the angle, that's going to be our direction. That's going to be the inverse tangent of, essentially, this is going to be, you could put it as 5.33 over 1, 79 point, we'll say 38 degrees. So the way I would finally answer it, my end result, I'd say that my net force on the object is equal to 5.43 newtons, and it is 79.38 degrees. You could specify that this is north of east, or you could just leave it as 79.38 degrees, formal polar coordinate form, however you'd want to specify that.